Alright, so in this problem we're going to compute the Galerkin finite element approximation by hand. So, well, let's see here. You type things with your hands, so couldn't you just type this up in MATLAB? And would that count? I mean, maybe, but let's actually do this exercise. So, what's the setup here? We are looking at the interval from 0 to 1, and we're using h equals a quarter. So we'll have 1/2. Nope, that's not right. That should be 1/4, 1/2, 3/4, and 1. And so this is going to be x0, this will be x1, x2, x3, and x4. And the x values go from x0 to xm plus 1, so we have capital M equal to 3 in this scenario. And that makes sense because in this problem that we've been considering, these functions vanish at the endpoints, and so our finite element basis is going to be hat functions centered at 1/4, 1/2, and 3/4. So x1, x2, and x3. Okay. So yeah, let's go ahead and do this. So AII, we've computed this already. This is 1 over HI plus 1 over HI plus 1. That's just given by the textbook. But this is a uniform mesh, uniform mesh. So all the H values are the same. So each HI is just 1/4. And so 1 divided by 1/4 is just 4. So this is 4 plus 4, which is 8. And this is for I equals 1, 2, and 3. And now AI, comma, I plus 1. Well, this is minus 1 over H I plus 1. Again, that's from the textbook. And that's just minus 4. For I equals 2 and 3. And likewise, AI plus 1, comma, I equals negative 4 for I equals 2 and 3 as well because of symmetry. Okay, so that gives us the matrix A. Next, we want to figure out the matrix B, and this is a hard, well, not the hard part, but it's, there's a lot of stuff you have to do. So BI is the integral from xi minus 1 to xi, f of x minus xi minus 1 over hi dx plus xi to xi plus 1, f of x xi plus 1 minus x over hi plus 1 dx. And so what is this? Well, f of x is just x, and 1 over hi is going to be 1 over 1/4, which is 4. So we can pull that 4 out front. Then we get xi minus 1 to xi of x times x minus xi minus 1 dx plus 4 integral xi to xi plus 1 of x times xi plus 1 minus x dx equals 4 times, and now we're going to split all these integrals up into separate integrals. We'll have x squared dx, and then let's see here, xi minus 1 is just a constant. The variables are x's. Integral from xi minus 1 to xi of x dx plus, and then again, xi plus 1 is just a value. We bring it outside. And then lastly, we subtract xi to xi plus 1 x squared dx. All right. Oh no, we have an entire another page of computations. And then is that the end of it? Nope, there's more after that. All right, let's keep going. So this is 4 times. Now this is just x cubed over 3 evaluated from xi minus 1 to xi minus xi minus 1. Now this becomes x squared over 2 evaluated from xi minus 1 to xi. Now we're going to add xi plus 1. And then now we have x squared over 2 evaluated from xi to xi plus 1. And we subtract x cubed over 3, evaluate from xi to xi plus 1. Alright, and now we actually evaluate this. Again, this is just really a whole bunch of calculus. I think the trickiest part about this section is understanding how all the pieces fit together, understanding sort of the big picture of this process, and sort of being able to picture the entire procedure in your head at once, rather than being able to do these computations. The computations end up not being too difficult, but they are a little tedious. So that's the only downside. But once you've done them, I don't know, you should do these computations because they do help you see the big picture better. And now we're going to combine like terms, x1 cubed over 3, xi minus 1 cubed over 3. Well, actually, I guess here we're just going to multiply everything out. 2 plus xi minus 1 cubed over 2 plus xi plus 1 cubed over 2 minus xi plus 1 xi squared over 2. Now we've also are subtracting xi plus 1 cubed over 3 plus xi cubed over 3. Alright, and now we're on to the last step of the general formula. If we combine all the like terms, we get 2/3 xi cubed plus 1/6 xi minus 1 cubed plus 1/6 xi plus 1 cubed minus xi squared. Then we multiply by xi minus 1 plus xi plus 1 over 2. And that's your formula. That's for I equals 1, 2, and 3. So now we can use this formula to actually compute these. And so let's see here. So for B1, you just plug in the different values. So at B1, this is the hat function centered at x1, which is, so this is I equals 1. So xi will be x1, which is 1/4. Then xi minus 1 is x0, which is 0. Xi plus 1 is x2, which is 1/2. So this becomes 4 times 2/3. Now this is 1/4 cubed plus 1/6, and this is 0 cubed, plus 1/6, this is 1/2 cubed, minus 1/4 squared, times 0 plus 1/2, and this whole thing is divided by 2. I'll just put a 1/2 on the outside that we're multiplying by. And then if you compute this using a calculator like I did, you get 1/16. Or you could do this by hand if you like enjoy working with numbers. I don't know. If it's just like a number computation, I'll just plug it into a calculator. So now for B2 we have x2 is going to be, or xi is, I is equal to 2. And so xi is going to be x2, which is 1/2. Xi minus 1 is going to be x1, which is 1/4, and xi plus 1 is going to be x3, which is 3/4. And hopefully in explaining that while writing down something, I didn't mix anything up. But if you do this correctly, you should get 1/8. Then B3, this is going to be 4 2/3. And now we have I equals 3, so xi equals x3, which is 3/4. Xi minus 1 is x2, which is 1/2. And xi plus 1 is x4, which is 1. And if we do this, you'll get 3 over 16. So you get 1 over 16, 2 over 16, 3 over 16. Thus, a xi equals b is given by, let's see here. So a, we have 8 minus 4 minus 4, 8 minus 4 minus 4, 8. Because we have, it's a 3 by 3 matrix, you've got 8s on the diagonal, and just off the diagonal you've got minus 4s. And now xi as a vector is just xi1, xi2, xi3. And this, or xi, however you want to say it. And then you'll get 1 over 16, 1 over 8, and 3 over 16 here. Alright, so then what we have is we have xi1, xi2, xi3 equals A inverse B, which is, again, I didn't do this myself. You could do this yourself, and it's especially if you're a little rusty on your linear algebra, it's probably a good idea to practice doing like inverses of 3 by 3 matrices. Well, then again, there isn't really a nice formula for that. There is a formula for it, but it's pretty messy. But you could just use a calculator to do it. So I guess this technically isn't being done by hand, but I don't know. I typed the numbers into my calculator using my hand, so I'm going to consider it to be by hand. 5 over 128, 1 over 16, and 7 over 128. So our actual function u of x is going to be 5 over 128 times phi1 of x plus 1 over 16 times phi2 of x plus 7 over 128 times phi3 of x. And here, phi1, phi2, and phi3, phi is the hat function centered at xi, and yeah, you just multiply it by this. And if you actually compare this to the exact solution we found in a separate exercise, it's like minus x cubed over 6 plus x over 6, I think. Whatever it is, if you plug it into a calculator and you actually evaluate it at, if you evaluate it at 1/4, you get 5 over 128. If you evaluate it at 1/2, you get 1 over 16. And if you evaluate it at 3/4, you get 7 over 128. So that sort of gives you some indication that that you actually didn't mess up in your math here, because this finite element approximation that we've come up with, it matches the exact solution on the grid points. And so yeah, this completes the exercise.